Thank you very much. My apologies to the experts in the audience. The talk will begin kind of with a review of very classical things, but maybe it's not bad to see old things again. So how does this work here? We want to look at these things. They have been around since the beginning of quantum mechanics. You take, as it turns out, a strong limit of the free Schrödinger evolution, and you go back with the perturbed one. And just like in Christoph's talk, you write ddt, and you integrate from 0 to infinity. That's not the only connection with Christoph's talk, because the main theorem the new one I will talk about is a technique that a PhD student developed, so just like in Christoph's talk. So you take ddt, you have this classical Cook's method. You see that this integral converges in the L2 norm, provided you have enough decay at infinity so that this is L2. And here you have the time decay. And because these are isometries, the density of this class is enough to conclude the strong limit exists, and they are isometries. And there's nice because they intertwine any function of the Laplacian with a function of the Schrödinger operator h. Take f any nice enough function so that, for example, it can be represented by a Fourier transform. Then this is kind of self-evident that you have this intertwining property. Then you apply the adjoint here. This becomes a projection. This is true of any isometry, the projection onto the range. I should have written plus minus there. And this is how you can kind of compute, quote unquote, from this a known object, this unknown object. All right, so this famous asymptotic completeness problem, if you want, is that the range are everything important and that there is no singular continuous component. And in the 60s and 70s, it was proven that under this short range, this classical short range condition, you have this asymptotic completeness. And when you do long range, then you have modified wave operators, something that will not appear in this talk. Okay, so it's interesting to note from the harmonic analysis perspective that this theory, as nice as it was, depended on something very, very simple. This is just Cauchy-Schwarz on the Fourier side. Okay? This L infinity of Fourier transform bounded by L1 of function, and then in one direction you apply L2, so you lose half a power. That's it. Okay? There's this trace lemma, has nothing to do with curvature. And so if you formalize this, you have a restriction operator, Fourier transform restricted to the surface. You dualize this. You dualize that, you do tt star, you end up with this type of statement that restriction followed by extension satisfies weighted bounds as long as the weight is a little bit faster than -1/2. And what is the relevance of that for the resolvent? Well, a lot, because your surface is actually the vanishing of the Fourier transform of this, which is a sphere of radius lambda, so the imaginary part of free resolvent is convolution by Fourier transform of surface measure. But turns out you don't need to take the imaginary part. This statement is still true for the full resolvent. That's the famous limiting absorption principle that was the key technical engine of that theory. It's really the key statement, that if this decays a little bit faster than a 1/2 power, then the resolvent on the spectrum remains bounded in this weighted L2 sense. And how to use this? Well, you apply the resolvent identity. If you pretend you don't stop, this is the Born series, you keep going. Well, that only really works if V is small. Is that this limiting absorption principle for the free Laplacian is then inherited by the perturbed one. And the way to see this, you just split V to even parts between left and right. And then you end up with these weighted statements. And indeed, if V is small in addition, then you can sum this all up. If not, what do? Well, then you run into this issue that you have to, I did it here, that you write the symmetric resolvent identity, why not? So you have U, basically U is V1/2 up to right? So on either side of the resolvent, then this is the identity in L2. The question is, does this inverse exist? And the point was then to show that Agmund did this when lambda is positive. Under this short-range condition, it does. At lambda equals 0, he didn't care about that, but we care a lot about lambda equals 0. It may or may not exist, and this is this fundamental zero energy issue that you have. You say exactly that zero energy is neither an eigenvalue nor resonance if this inverse exists at zero energy, which may or may not be the case. Now then it's natural, and my collaborator on this issue is here, Alex Ionescu, and I looked at what happens, Goldberg and I did a little bit of this first, what happens if you replace this very primitive trace lemma, which is just L1, L infinity, Fourier transform with Cauchy-Schwarz. If you replace this with something a bit more sophisticated with the Stein-Thomas theorem, and Koenig-Ruiz-Sorg had obtained the analog of that for the resolvent. Remember, there is a very close link between these two, because if you dualize TT star that, you obtain convolution by the Fourier transform of the surface measure of your surface S, which is the imaginary part of the resolvent. For the special case of the sphere of radius lambda, that's where the symbol, the Fourier transform, becomes singular.
This is what we call uniform Sobolev inequality?
Yes. That is what their paper is, uniform Sobolev inequality. Right? And so in the paper with Alex, to formulate the result, it looks a little bit technical, but it's just for the sake of honesty, I want to give you the correct statement. So you have the short-range condition, which is the dj. What is that? That's a dyadic size of size 2 to the j, starting with the ball of radius 1 around 0. D0 is just a full ball, and then you take the dyadic shell. So this is the sharp short-range condition. And then you have this other condition which mixes, it distinguishes between local singularities, which are d over 2, take dimension 3 or larger, then this is d over 2. But at infinity, you require less, d plus 1 over 2. All right? So this distinguishes local singularities from decay at infinity. So the theorem with Alex was this, that if the potential splits into two halves, one corresponds to the classical pointwise short range via this norm y that we just had. The other one is this mixed d over 2, d plus 1 over 2 condition. And then you have Agnon-Kato-Kuroda theorem. So you have what you expect. It's a little bit delicate whether in the absolutely continuous spectrum you may have eigenvalues or not. So this, first there is Ionescu-Jerison for d over 2 potentials, and then under the condition star, Koch and Tataru showed no positive eigenvalues, correct? Yeah. So note that this requires less than d over 2. This d over 2 condition will haunt us throughout the talk. It corresponds to an x minus 2 decay, whereas the short range is x minus 1. And the way I see this, there are these two different rates of decay which are critical, quote unquote. And x minus 1 is this classical one. And the way I distinguish them intuitively is that short range, long range really is a high frequency distinction, whereas d over 2 is the scaling invariant condition, and that is what you cannot avoid when you, well, first of all, a scaling invariant, but also focus on zero energy. Okay, so rather than high energy, if you want all energies, in particular low ones, then the cutoff is not the classical x minus 1, it's x minus 2 decay. Namely, the d over 2 is then the critical number. And interestingly enough, this condition on the previous slide, this one here, the d plus 1 over 2, is sharp by an example that Alex constructed with Jerison, which is anisotropic. It behaves differently in different directions. I find this very interesting. It's reminiscent of a NAP example, where you have a parabolic type behavior, xx squared.
So what's this an example of?
This is well, Alex should explain, but this is a potential that has no singularities at oscillations, and it decays at this rate, and it decays differently. X prime are the other directions, x2.
Yeah, then what does it do?
You have embedded eigenvalues in,
Embedded eigenvalues
yes, in this continuum spectrum, yes. Yes. So
that's very special, right?
Yeah, it's a potential, it's an example of a potential.
Yeah, but if I were to perturb it somehow, then would I not expect my embedded eigenvalue to disappear?
yes, you would expect it to disappear.
I mean, I would.
Yeah, but it does show.
The question is how robust it is. That's my.
It depends on oscillations, so it's non-robust, right?
Oh, I see. That's the absolute value. So, but you have oscillations in there, right? I mean, that's the absolute value, but.
That's the absolute value.
You have absolute values like that, but I mean, in general, you might expect by, then we go to the rule, but perturbations will
But
make it a resonance.
it does prove that the condition is sharp. Right?
Agree.
But again, I was at one. I think at one, if I remember well.
But it's an eigenvalue embedded in the continuum, right?
Yeah.
No, yeah, so, okay. No, it's interesting, there are, I mean, of course, I know such examples, but I've also been led to believe that they're exceptional.
So one thing that's not understood here is how to construct singular continuous spectrum. Nobody has done that, right? So that's an eigenvalue, but singular continuous spectrum, which if anything should be more robust than an eigenvalue, that nobody has done. And from when we did this, I remember the discussion with Barry, and Barry actually believes that power d, p equals d, should be the cutoff for a singular continuous, not d plus 1/2. And that's not understood. All right, so then it's perhaps also interesting to ask what happens to the deterministic theory if you consider random potentials. And it turns out that for random potentials you can shave off half a power of the decay. And so let me quote a theorem of Jean. He did this in the discrete case, 2 dimensions, so the reason really what he did works in all dimensions. But if you take the discrete Laplacian and you look at its symbol, the symbol is not a nice sphere. You have energy levels where it has some form of degeneracy, curvature can vanish and so on. So that is the only reason why he restricted here to 2. And it's also the reason why he had this strange, why he has to cut away the middle of the spectrum. This is counterintuitive, that he has to cut away the center of the spectrum. And the reason is that if you look at the symbol,
The very surface is nasty there.
it's just a square.
Yeah,
It's a square, and he has he wants a diffeomorphic change to make it nice and round. So it's a technical issue. It's a little bit unnatural.
Well, not necessarily. I mean, I understand it's a technical issue, but it can be a tough technical issue.
And so this is what he shows. He shows that almost surely, if you stay away from 0, the edges of the spectrum, then you have asymptotic completeness.
So this probably does not occur in the continuum.
In the continuum, no. In the no, in the continuum, if you write
You wouldn't have that problem.
as a field of bumps, you don't have these squares, and so you don't have that. In fact, this theorem was motivated that Ego and I did before that, where we had somewhat different potentials and we constructed modified wave operators by Hermander parametrics. But it was also motivated by work of really Wolf Schubin that I then completed after Tom tragically died. And I probably completed it in ways that Wolf would not have liked, but that's a different story. So key there was an estimate of this type, where you have the restriction operator. We had actually restrictions to delta neighborhoods of curves. So you take your random potential, it decays like that. You restrict it to a shell of size n, and you have extension and restriction operators on either side. And then you pay root n, but you gain this back. And that is essentially sharp. Our proof back then used curvature, used these Bochner-Ries Pfefferman type rectangles. So we had a geometry of just like in Cordoba's proof. of Bognor-Ries in the plane, but Jean then realized that this has nothing to do with curvature actually. He used something that he was very well familiar with from the lambda p problem, namely these dual Sudokov entropy bounds, which just answer the question of how many balls of radius t you need relative to some norm to cover a perfectly round Euclidean ball. There is something, the entropy bounds, all right? And so the message here is that the power is shaved, you shave 1/2 off. We just spoke before about restriction instead of trace. The previous slide was essentially just trace. You can take Bougain's random proof and you look at it deterministically, you get exactly the old Agmond theory back. Right? But what then try and inject, for example, what Alex and I did. And so Jean looked at that back when he did these things, and he found somewhat strangely only an L3 condition, little L3 in Z2, which is not what you want. N minus 1/2 corresponds to little L4. But
so that's a weird thing. I mean,
yes, but there is a reason for this. It's the anisotropy, similar to the anisotropic example that Alex has with Jerison, but although the connection here is not a close one, right? It's just philosophical if you want. The reason that so you want this type of bound. This bound is what you put into your Born series, and unlike in Agmond theory where you split V to equal parts between the neighbors, in this you split the resolvent to equal parts to the neighbors, and in the middle you have this random potential sitting. That's what this is, right? And then if you TT star this, don't take these details too seriously, Tom will immediately recognize this. This is like a self-energy loop. You end up with two potentials, the same potential Vn squared. And that is saturated by a NAP example. You will get size 1 for this if V is a potential. You lose the randomness completely here. If it's a potential that lives on a rectangle of size n by root n. And that's an L3. If you work out the numerology, it amounts exactly to L3, and Jean notes that. But then he makes this strange comment that I don't understand, and I hope to understand better here at my visit, that he wants to renormalize this away and then use the Carlson-Schilling, which is the sharp restriction in the plane, which is known, to get L4 back. That all sounds very reasonable, but what I do not understand is that the renormalization he proposes depends on the energy. Has to depend on the energy. If you are in the Anderson model, then Vn squared is a constant. And then this is a very nice function of the energy only. Here it is not. Okay? In fact, if you work with little L4 potentials, this becomes a little L2 potential. Actually, it's a little bit better because Jean is willing to give away n minus epsilon losses. So a little bit of a logarithmic leaking doesn't matter here. But so I do not understand exactly how you would renormalize here to. He does say one should remove these self-energy loops, but how that works, it's not so clear. All right, now let me go to the LP theory. This is Yajima's work from the 1990s, and he proved that the wave operators don't just make sense on L2, they make sense on LP. But it's a little bit delicate. You do have to remove, well, not remove, you have to assume that zero energy is regular. Remember, we had this condition that, what does that mean? It means exactly that this thing can be inverted at lambda equals 0, and you know from theory that it can be inverted for all others in the positive spectrum. So that's Yajima's result, and if you do have a zero energy problem, you cannot be LP bounded for very good reason. Okay? And just for the sake of completeness, I want to mention that in dimension 3, or record, he needs -5 minus epsilon. And because of the intertwining property, if you have any dispersion relation omega h, you can recover dispersive estimates, pointwise Stricherts, whatever you have, from that, because, for example, of this line, right? It's obvious. You can transfer LP bounds because of this. And so how does he do it? Well, he starts off, at least formally, you can keep expanding the Duhamel formula. So you end up with this. And the restriction property of the Fourier transform comes back in here because the cleanest way of making sense of such an expansion, at least if V is small, is by using the Kiel-Tau endpoint. You can use other things, of course. But with the Kiel-Tau endpoint, it becomes very clear that this, and this is a typo. This is 3/2, not 3. That's bad.
This 6,2 is what?
This is Lorentz space, 6,2.
Okay.
And this may look like a technicality, but such small details can be important. Okay, and what? So V needs to be as a multiplication operator bounded from here to here, which is clearly not L3, it's L3/2, because 2/3 plus 1/6 is 5/6. All right. So here I have 3/2, you have 3. So this series converges, in particular, if the 3/2 norm is small. Right? So you have that. And what do you do with this? Well, then you grit your teeth. You have to somehow make sense of this. So not surprisingly, you switch to the Fourier transform where you have explicit formulas. If you work this out, you at least end up for everything a Schwartz function, you get these formulas. And you put an epsilon in here, which means what exactly? It means that in these formulas, you put a decaying weight, like e to the minus epsilon t minus s1, and then you let epsilon tend to 0. So you go epsilon above the spectrum, which is standard trick. Yeah? That makes the denominator not vanish, and you end up with these formulas, and I don't want to overemphasize them. They kind of make your eyes glaze over, but it's all right. It's just to show you that there is nothing much going on. It's very explicit. And then if you undo the Fourier transform here, notice carefully, that's important, that you don't just have kxy, fy. You need to realize that the correct structure here of your kernel is always this convolution. It's a strange action, right? It's not a clean convolution, it's x minus y. And if you write the kernel this way, and this Yajima all realized, then you have something that's a bit reminiscent of a Radon transform. Right? If you do a Radon transform where you integrate along planes, you have a function that depends on your position on the line and the direction. If you Fourier transform along the line, in your Radon transform, you get exactly the Fourier transform of the function on that line. That's this famous relation of the Radon transform. So here you have something a little bit similar, but you have a Hilbert transform because you don't do minus infinity, infinity. So you only do 0, infinity, and you have this additional s, which is very important. So this is what you have. And so if you just believe whatever there is to believe, you have explicit formulas, and what do we do with them? Well, then the first term in your expansion of the wave operator has this explicit form. It's this function L that we just had. And if you look at it, you see that you can bring in a reflection. You just change variables. R becomes R plus 2 omega x. You stick it in here. Lo and behold, that's the expression of a reflection on a plane. And then you have this creature, which you just call G1 x dy omega. 1 because that's a 1. And what is G1 exactly? If you unravel the meaning of this, because you're integrating along a line, this y has to be integrated along a line. So G1 is this function, or rather it's a measure on the line in direction omega. That's G1. Question? So, and also evidently this G1 satisfies this bound. All of this is completely explicit, right? We had a formula, we know how to compute L from V, we see as long as we do this, and this one has to observe that you look for your kernel in this form, okay? Then you have L infinity norm in X, measure in Y, bounded by the L1 norm of L along the radius, averaged over the sphere. And this you call norm L. And so immediately you see that this first term in the expansion of your wave operator satisfies an LP bound, right? Because if you start taking LP norm here, you put an L infinity on this, the reflection is an isometry, it doesn't change the LP norm, the translation doesn't matter, and everything else gets integrated out, right? So you put kind of L1 in y, L infinity in x, first L infinity x, L1 in y, and then L1 in omega, and you get that. And then you're left with the question of how to bound this L. And we'll get to that in a moment, but this should motivate. I only understood Yajima's LP theory once I saw this, because here, when you see this, you kind of believe that there is an LP bound, right? But you should believe a little bit more. You should believe perhaps that the higher W's, the next terms in this expansion, W2, 3, might also satisfy a representation of this form, where W10 becomes an average in this sense of translations and reflections by planes. Which maybe, I mean, Tom is in a better position to judge, but is this physically maybe appealing? What does the wave operator do? You send in a wave, it reflects it, translates, I don't know. So there is a representation of that. And now we have to bound L. So there's a slide that explains how to do this. You define a weighted L2 norm on the ball, and then weighted on dyadic shells. Then here are some fairly obvious embeddings. L3 halves, remember, is the important scaling invariant case. Why do I call it scaling invariant if you haven't seen this before? If you have minus a plus v, then you change v by, say, this. But because of the Laplacian, you have to, so your v lambda should be this. Okay? And that's exactly L d over 2 of Rd invariant scaling. All right? So that's the role of this L d over 2 that I mentioned before. So that's why this is highlighted here. And everything here on this slide and previous slide is three-dimensional only. Okay? That's an important point. And in fact, Yajima showed that for small potentials which are in the class B1 plus epsilon, notice this falls short of the critical one, which is B1 half, B1 plus epsilon, then each of these terms is LP bounded. All right?
So does the dot just mean you can forget about the ball?
Yes, sorry. The dot means forget this and do this from minus infinity to plus infinity. Sorry, I should have said that. Okay? All right. So here are these results with my former student Becciano, who deserves a lot of credit. So let me first say the theorem and then a little bit the history. All right? So the history, first, what's the theorem? If you take v b1 plus, so that's 1/2 power better than what you would want. You want x minus 2, which is the LD over 2 or L3 halves condition. This is three-dimensional, which you see here. We have to give away in this theorem a 1/2 power. So this would be like minus 5/2 decay, which is much better than what Yajima had, because Yajima had minus 5 decay for something like this. Then, not only do you have the structure formula for the first term in your expansion of the wave operators, you have it for the full wave operator. So you can write your wave operator as the identity plus an average of translations and reflections. And in particular, if you have any Banach space which is invariant under these operations, and in fact with a quantitative bound, then the W plus minus, they're both bounded on such a Banach space of measurable functions. All right? That may be not immediately clear from this. The reason will become clear later, or I should just point out the special feature of G1. G1 is not just any function in X. If you look at this, this is the indicator function of a half space. All right? So what you're really doing is you need to be invariant under restricting to half spaces. And then just for the sake of completeness, I want to put down a quantitative statement here. This is not very nice, it's just less than infinity, but you want a bound. So how can you bound this norm of G, of the structure function? And so we have this. If you are a bit better than B1, you're B1 1 plus 2 gamma, then we have funny numbers coming up. So the bound gets worse and worse as you approach 1. Ideally, we would have this with 1/2, not 1. That's what can I do? And so what enters into this bound on the structure function is the size of the potential, but also, of course, a certain bound on the Biermann-Schwinger operator. And so this is it. This M0 is the bound from, as an operator bounded from L infinity to L infinity, which is legit because this creature is bounded from L infinity to L infinity if V is a 3/2 essentially, right? 3/2 1, Lorentz space 3/2 1. And zero energy, not having a zero energy resonance means that at zero energy this holds. Ideally, we would be able to take this and put the rest in here. All right? This is essentially, I do mention this very nice paper of Igor, who's here with us, Igor and Terry. What they did is they got rid of Fredholm alternative and compactness argument and made limiting absorption principles effective. I imagine that what they did in their work can resolve this issue. Right? Somehow you transfer it to L infinity, you would get quantitative control on this.
So what is the statement of Wojciechowski tau?
Igor, you're in a better position to say. Okay, so if you put yourself at energy bigger than epsilon fixed, then they can bound the resolvent, which is exactly right with the potential. So they have weighted L2 estimates of the perturbed resolvent, but with quantitative bounds that depend on derivatives of the potential size of the potential, but not an inverse of something. The standard limiting absorption principle goes by Fredholm alternative, right? If it failed, then you would have a violation of compactness, so that's soft, okay? But they actually, by integration by parts, by Kalman estimates, gave concrete bounds, made it effective. Say it again? No, not L infinity, weighted L2. You would have to transfer this to L infinity, but that sounds to me more like a technical problem, okay? But it may or may not be possible. I have to look more carefully. What is your feeling? Do you give away so many weights? You do give away some weights, right?
You should be.
Okay.
There is no conceptual obstruction.
Okay. So let me mention that theorem cannot hold in 2 dimensions. This is a 3-dimensional theorem. I don't know about 4 and higher. But it cannot hold in 2 because Yajima already observed that the LP bound that he gets, he needs to stay away from 1 and infinity. I have to understand better why, whether this is really intrinsic or not, but there is clearly an issue. You can't hope to generalize that immediately to 2 dimensions. If you had that in 2 dimensions, well, then you would have LP bounds because of this stuff, right? Who cares whether you're L1, L2, L3, all right? And secondly, this also has to clearly fail if zero energy is not regular. So if you have a zero energy eigenvalue resonance, which means what? It means that this is infinite. That's exactly what that means. Then you can't have that theorem either. We know that too, because if you had it, then you would have, for example, dispersive decay, L1, L infinity, just like the free case, which you cannot have if you have a zero energy problem. All right? So this is a fairly tight rope that you're walking here. And in his PhD, Benciano introduced, I think he was first to really do the Wiener theorem on the level of operators. Michael Goldberg and I in 2003 had done this still in the scalar case on the line in a purely one-dimensional problem. But Benciano did something quite different. So what is the classical Wiener theorem? How much time do I have? So that everybody knows. Actually, Wiener did this on the circle. You have the Wiener algebra, the convolution algebra of functions with absolutely summable Fourier coefficients. If 1 over the function makes sense, so if f doesn't have zeros, then 1 over f still has absolutely summable Fourier coefficients. You cannot do that on RD, on the line, because the function vanishes at infinity because of Riemann-Lebesgue. So instead you formulate it like this. You join the delta distribution.
I'm not following. What's the statement here?
So you take an L1 function and you want to solve this. Delta plus f, you want to find a g such that you can invert this in the convolution algebra. When does this inverse exist? Well, if and only if you can take 1 over that. So if and only if 1 plus f hat is not 0. The necessity is clear because you can just Fourier transform that.
Yeah.
And then it turns out that, okay,
That's sufficient.
that's also sufficient. That's this famous Wiener theorem, and it rests really on two things. It's a uniform L1 modulus of continuity under translation and the vanishing in the L1 sense at infinity. These two things. It's like in Asela Ascoli of equicontinuity and compact support. So here I give a version of what Bechiano Goldberg then did on the level of operators. So let X be any Banach space, which in the next slides will be L1 on R3, okay? And Wx is an algebra of bounded linear maps from X to L1 Rx. Notice it's not L1 of bounded operators on X. It's larger. It's bounded linear operators from X to that. And it is a convolution, has a convolution structure as long as you stick in a test function, an f, all right? And so you throw in a unit, you call this the larger algebra, and you have a Fourier transform because of this L1, and it clearly satisfies this bound. And so the abstract Wiener theorem of the way it appears here on the slide is from the paper of Bechiano and Goldberg in CMP in 2010. You have a uniform modulus of continuity under translation in this algebra, which has the obvious norm, right? It's just a norm as bounded linear maps from X to L1 Rx, and vanishing at infinity. Then if the identity plus the Fourier transform is invertible in as a bounded linear operator on X, then you can solve the convolution problem. All right? Then 1 plus t has an inverse in this algebra. All right? And so how do you apply this? I find this kind of neat. So this is, again, lifted directly off of their paper. It looks a little bit magical. Take the free resolvent at energy lambda. It has, in 3D, has this explicit form. Then define an operator, but this time as a Fourier transform, which is the Biermann-Schwing operator, resolvent times potential. If you undo this Fourier transform, you evidently, because you get a delta function at absolute x, you end up with this, right? Take a Fourier transform lambda of that. You get the measure on a sphere. So you will end up with this. And what algebra do you now have? If you just blindly compute dx d rho, you end up with this creature. Clear, right? You just integrate in rho, then you get polar coordinates, so you end up with this. And you recognize that if you isolate this integral in y, rather in x, and you soup in y, then you get what Igor and I, in our second joint paper, called the Kato norm. And we proved dispersive estimates on the small Kato norm. What these guys did, because of this Wiener algebra technique, they were able to treat large Kato norm potentials because of what's on this slide and the previous one, okay? So how should we think of this Wiener theorem? And that's so important, but also evident, right? It's a vehicle to some divergent series. When this is small, you can solve for G just by taking a geometric series. So therefore, this is a vehicle to sum a divergent series. And that's exactly how we use the Wiener algebra technique to sum this divergent series here. This divergent series, we sum this by Wiener algebra technique. But it's unfortunately not as simple as this, okay? And how successful I will be at convincing you that it's easy to convince you perhaps that it's a bit messy, less that it's actually quite clean at the same time. So in order to...
But you can do this.
You can do this, but not in such a... this is much too simple-minded.
Okay.
The structure is more complicated. And so I feel I'm either sweeping things under the rug or I'm honest about it, so I try to be honest about it. So what you first do is you introduce an ambient algebra, which point-wise you need 9 variables actually. It turns, and why do you need 9 variables? That you observe with some hindsight from this structure here. Because what's staring us in the face here is somehow this, by convolution, gives you that. But if you notice, there's always this difference, whereas how do you generate this difference here? To do that, you need to introduce a third variable, which in this formula happens to be 0. So you have psi minus 0 sitting there. But if you then jump over that hurdle, you see that you really need to consider 3 variables. And just like on the previous slide, when you start in the Fourier transformed version, we start in the Fourier transformed version. So you have kernels y. The Fourier transform of y in eta has to be uniformly in eta bounded as an operator from L infinity to L infinity, which is exactly this. You have L1 in x0, L infinity in x1. This is input, output, and this is some spectral variable. Okay? Input, output, spectral variable. Those are the 3 sets of variables. And you introduce convolution in y. But here you have to do this in tempered distributions. So you multiply like that, which you can do because you L infinity, then as tempered distribution you undo that, and that defines a structure, a convolution structure on this Z, and that turns it into an algebra. Right? In this norm. And then you introduce, you need this strange semi-normed space, which looks a little bit scary. It's all measurable f, such that the potential times f is in one of these B sigma classes, these weighted L2 classes. And that's your semi-norm. And then you introduce another space, which is that thing by L1 in the spectral variable. Okay?
That's complicated.
Yeah. And then your algebra, which is the one that makes things work, are all kernels in Z, which under contraction by an L infinity function, we call this contraction, is in this X space, which is, we want to think of it, actually, this makes everything work, as strange as it is, but we want to think of it almost philosophically like this. Because V is in B sigma. Take V to be a B sigma potential, then L infinity is clearly a subspace of this. In fact, it stands here. So ideally, we would want L1y, L infinity x instead of this. But you can't do that. It does not work, okay? But you can flip the variables. You can do the larger space where the smaller norm is L infinity x preceded by L1y, okay? That you can do, but it's not useful. So this is the structure that we have, and the contraction operation between a variable of a kernel of 2 variables and the kernel of 3 variables has to be this, okay? And then it's set up in such a way that the x space norm of this contraction is bounded by the y norm of t with the x space norm of x. And that is what y into an algebra under all these norms. And why is this relevant? So this, yeah.
Prove that your theorem with
Yes. That's the framework you need to make it work. And Bejarano had actually published a version of the structure theorem a couple of years ago, which turned out to be completely flawed. And one of the things that broke down there was the wrong choice of algebra. And so,
you have to set up the right algebra.
You have to, yeah. And so this by itself, VR0, is the Biermann-Schwinger operator. Now, that's not enough here. You have to do a modulation in output and input, which are exactly inverses of each other. Okay? And then this star operation allows you to build the higher WNs from the first one, from W1. So you can build T2, W2, T3, W3 by means of this star operation. And this is what I said about the three variables, one of which is always set 0. But the star operation requires you to use that. Okay? Without it, you cannot unravel this structure. And so there you have it. From this T1, that is like a Biermann-Schwinger, but with modulation, and the modulation depends on the energy. Reminds me of this question about renormalization. The self-energy loop depends on the energy, whether that's a silly statement. You can build all of your wave operators. So the key to understand, of course, is not these individual ones. Remember, you can sum them if the potential is large. The key is the end result, which is W, and that is formulated just like these. If you look carefully, they look exactly the same with one difference. There is no N here. And if you remember this formula of VR0 modulated, well, the big potato is the one with RV instead of R0. None of this is surprising, right? And so the resolvent identity on the level of these guys now reads as an identity in the convolution algebra. And this is the key problem that we have to solve. We have to show the invertibility of this creature in the algebra Y. Notice the total analogy to what we did in the first half of the talk. We needed to invert the Biermann-Schwinger operator, which has been around since the Stone Age. It's something like this, right? You have to invert. Here I chose the symmetric resolvent identity, but you can put the potential on either side, but then you're not in L2. That's why I used the symmetric one. So you have to invert this resolvent identity. You have to take the inverse of this thing to get the Green's function. But we have to solve the analog in our algebra, which is this.
I'm sorry, I probably lost the main point here, but why do you have to solve it in the algebra?
Well, I tried to say a little. Well, first of all, because there are a number of ways to answer your question. Because so the shortest answer is because we deal with the wave operator, and the wave operator is much more complicated than the resolvent, right? And these formulas show you that
so you can control the whole
everything at once.
So you can control
everything at once.
In a natural way.
Yes.
You
Not
products and so on.
yeah. You don't have individual lambdas. Yeah. The wave operators involves all of the energy.
So that product structure, or there's some kind of multiplication.
Yes. So resolvent identity is point-wise in energy, but this is kind of Fourier transformed in that, all right? Because if you note, you have to treat all energies at once. These constituents of your series, your Dyson series, or the wave operators, each have a structure function, Gn, satisfying all the bounds you want. So this recovers with more information what Yajima observed, that for small potentials which are B1 plus epsilon, that you get LP bounds. But we also get structure for this. Again, I repeat myself, I don't know how much you want to see, but I want to emphasize this. You may ask, well, how do you find the structure function? And the answer is you find it recursively from the first one, from G1. And here is the formula. How illuminating this is, I don't know. But not surprisingly, this Gn is an average of the G1s, but you can't get away with your potential V alone. The potential V is multiplied by this guy, which is the kernel of the previous one. So it's an inductive procedure that rests on these two innocent-looking lines, where these...
That line there, the bottom line,
yes.
bottom formula displayed. Yeah, so Where's the F there? I'm kind of
Look, these are the wave operators,
Yeah.
but I identify them with the kernel, where the caveat is that you don't have wxy integrating fy, you have wxy integrating fx minus y.
Okay.
That's just the rule. In these structures we set up, the kernel, if you notice here, you have a zero. The zero integration in that's exactly what this is, indicator, because indicator hitting this three-variable kernel is this contraction notation, and contraction means integration. So you hit this with this indicator, just integrate that variable out. Then you note that this is given by this convolution in the Z algebra if you want, but we actually now know from you are in the Y algebra. So this is in Y. Then you note, just by the way, is that you can, the input variable of this is the input variable of that. So this is a contraction of this hitting that. But this hitting that is the kernel of Wn minus. The plus is just because of plus minus in time, all right? So how do you get the kernel of this? You contract this fellow, which is this completely explicit expression here, which has the free resolvent in it. You contract that by the kernel of the previous term in your Dyson series. And just for the sake of convenience, because I didn't want an n here floating around, I just call this f epsilon y prime. And what does this notation mean? It's the G1 function, which was this totally explicit thing with L and the Hausdorff one measure on a line, yeah? But not with V, the given potential. That has to be multiplied in this sense by that guy, and then you have to average out in Y prime. And this doesn't do any harm, because you just take, so you immediately, is that written somewhere? No. If you take, what do we have to do? L infinity in then you take measure the total variation in y. Okay, so just by Minkowski, these guys satisfy all the bounds you want. All right, so that's how this vehicle runs. But again, I want to show you kind of how this really works. So, what is our Wiener algebra theorem? This is, if you want, an abstract theorem in our algebra Y, as defined on a few slides before. So you fix a potential in sigma, and you have to define Y with this choice of sigma and V. Remember, we had this semi-normed space, V inverse B sigma. This is your choice of V and sigma. And now suppose, again, you have these two conditions. One is modulus, what is called equicontinuity relative to translation, but in the Y norm. So this is what in L1 was just uniform modulus of continuity under translation, and vanishing asymptotic at infinity. Okay? And this is delicate. Our first version of the algebra had in it an L infinity x followed by L1y, which is nice to have, but then we realized that you don't have this because of this L infinity, so we had to remove it from the algebra. Hopefully now we have a correct version of the algebra. And then assume that in the bounded operators on L infinity, you can invert the Fourier version of this, right? So you want to invert 1 plus s. So imagine that you can do this just like in Wiener's condition. And where do you invert this? This has to be pointwise in eta, just like in the Wiener algebra on the circle pointwise. You have to be able to divide function or divide by it. But you need more. You need that this inverse is from identity plus u eta, where u eta is in the Fourier transform of the algebra Y. You can identify what that is. You just write it down. And uniformly so. And moreover, you need uniformly continuous, this thing. And then you're invertible under Y. So this is much more complicated, even though you can say, well, it's a technical variation. True, but many details. Right? And not surprisingly, you can make this quantitative. If you have quantitative control of that, quantitative control of that, quantitative control of all of this, then you get some kind of quantitative, what you get? You get a bound on the norm of S in Y, which gives rise to this. to these funny numbers. So where am I going with all this? This is the last two slides. So we really want a scaling invariant version. And why do we want this? Because
so this is not quite scaling invariant.
no, the theorem.
Epsilon, right?
No, by a half.
Oh,
by a half plus epsilon, we miss scaling invariant. We would need to be in b dot 1/2, but we are not just not dot, we are b1 plus. So we miss by 1/2 plus and the dot. Okay. And we don't know how to do this on the level of these weighted L2 spaces. But we wrote a little paper in January where we noted that you can create some kind of monster norm. You take a Schwartz function V, you do this creature, which is just the L function that arises in the G1 structure function. This is Yajima's notation. And then you take that, but you slice over planes and you integrate over planes. This turns out to be a scaling invariant norm. But it turns out not to be just a size condition, not surprisingly, because of the Fourier transform. You can bound this by that. And this is the best I know how to do, Bechian and I know how to do. You take a little Paley decomposition on planes, you pay half of a derivative. So this is not just a decay condition, you need half of a derivative. Okay? And with this crazy, by the way, if you look at this, it's not even clear that Schwartz functions little v have finite b norm.
Isn't that something like norm of the Radon transform?
Should be related, but remember this is not quite the Radon transform because you don't go from minus infinity to infinity. That would be nice. Then this would be a t derivative of the Radon transform. Yeah? But it's not from tacked onto it, which is dangerous because you have an L1. So Hilbert transform on L1 is not good. Our theorem simply says that under the scaling invariant condition, if you're small, then you have what you want. But this is not good enough. We want large. And that requires you to do all the spectral theory that we rely on for our structure theorem, because there are many things I didn't mention. You see, if you look at that, where do you get this from? Where do you get that this has an inverse? Well, that's a spectral problem. In particular, you have to look at zero energy. All right? That's where you fail if zero energy is a resonance on eigenvalue. Right here. But to prove uniform continuity, to prove these bounds, well, we have to rely on what Michael Goldberg and I did, what Alex and I did, what Alex and Jerrison did, excluding positive eigenvalues in big L3 halves class, even though we fall short of the L3 halves. But any hope of making this large, you need all of that. Okay? So there are several layers here. If you know. All right. And ultimately, where we're hoping to go with all this, if we have large scaling invariant, we want to make the potentials time dependent. Okay, because we want this scaling to depend on time, and then you solve a scattering problem from time to infinity where you have two different times. You have the time of your PDE, and then you have the scattering time. But this is for the future. And the reason we want that is because in nonlinear problems, if you take a u to the 5 wave equation, for example, you linearize about a soliton, W, you get linear problems with time-dependent lambda that are exactly critical. Yeah, critically rescaled. So you have no choice. But then Hao will complain, of course, that in such nonlinear problems, zero is a resonance and an eigenvalue. It's unavoidable because that scaling comes from symmetries. What can I do? Okay, so the place to start, for me at least, to understand this type of dynamics of time-dependent potentials would be, that's all I can do is. Even that, at the moment, we're falling short because we don't have a, large potential version of this. Thank you.